Students, this lecture is on to discuss classical distribution function or Maxwell-Boltzmann distribution function. So, after unit 1 and 2, we are now familiar with the issue of basic terminology of stationary mechanics and the canonical ensemble theory. So in the canonical ensemble theory, we discussed about Boltzmann factor. So using that Boltzmann factor, we have one term, that is Maxwell-Boltzmann distribution function, that we would like to see in this presentation. So we have a system of gas. There are a number of molecules. These molecules are at temperature T. Say they are placed in the container having volume V. So molecules are at high temperature. Temperature is very high. So molecules are distant apart. So they are not feeling each other, or there is no interaction among these molecules. And since molecules are distant apart, so density of gas is very low. So in that situation, what happens? This intermolecular separation is very large in comparison to de Broglie wavelength of a molecule. So in that situation, we can handle this issue using classical distribution function or Maxwell-Boltzmann distribution function. So in the high temperature region, your molecule follows this kind of distribution function. The probability of finding any state, say epsilon, is proportional to e power minus beta epsilon minus mu, which is chemical potential of the molecule. So we would like to derive this distribution function. So we have molecules which are basically identical. So n number of molecules are there. All these molecules are identical, but according to classical distribution function, they are distinguishable. Any number of molecules may be placed in a given energy state. So any energy state you talk about, and the number of molecules that can be accommodated in that state may be 0, 1, 2, 3 up to infinity. And there is no symmetry requirement with the state of these molecules. So exchanging molecules coordinates will not require any symmetry related issue. So we have gaseous system where number of molecules and molecules are occupying a volume B of the container, and it is at temperature T. Total energy of n gas molecule is capital E. So in that situation, we can write total number of molecules according to this relation. So R is any say state over all possible state, number of molecules say small nr, which is summed over all possible r to have total number of molecules capital N. And total energy of these molecules is capital E. So each energy state, say rth energy state has energy value epsilon r, and number of molecules in that state is nr. So nr multiplied with epsilon r summed over all possible values of r will lead to a total energy capital E. When molecules are non-interacting, in that situation only you can write total energy in this fashion. Okay. So now we can write partition function for this n gas molecules. We can write partition function z in this fashion. So all possible are e power minus beta epsilon r nr. So this term we are familiar with. See, this is the basically Boltzmann weight corresponding to probability of finding energy state epsilon r at temperature, inverse temperature say beta. So this term we can write in this fashion. So equation 4 we can further write in this fashion: e power minus beta epsilon 1 n1 plus e power minus beta epsilon 2 n2 and so on. So all possible r, say r maximum value of small r is capital R. Okay. So from there we can determine average number of molecules which can be accommodated in a say rth state. So nr e power minus beta epsilon r nr, okay, divided by sum over r e power minus beta epsilon r nr. Right. So this term, the denominator is a partition function. That is question number 4. So nr and corresponding weight, Boltzmann weight. So Equation number 6, further you cannot find any Sth state in this fashion. Okay, for any Sth state, average occupancy can be retained in this fashion. Here we have taken derivative of log of z with respect to epsilon s. So epsilon s will be any of these values. Say epsilon s is say epsilon 3. When you are taking derivative of this z function, log of z function with respect to epsilon 3, what you will get? So you will get 1 upon z first term, then second term what you will have? Beta and minus beta and n3. So this is what? N3 you have. Minus beta means minus 1 upon beta you divide with. So you will have derivative of ln z with respect to this will give you this term. So from equation number 7 you can get equation number 6 for any arbitrary s. Right. So this we are trying to see further according to this description. So n number of molecules are there, they are distributed in different energy states. So at time t, here this is the distribution of your molecule in various energy state. So according to relation, this equation number 2, number of molecule is fixed, number of molecule is fixed. So possible ways in which these molecules can be distributed in possible energy states, different energy states, Rth energy, all possible R values of small r values of energy states. So these are the possible distributions where each molecules are distinguishable and identical. Right? So this is capital N divided by small n1 factorial, small n2 factorial, and so on. So this is the possible distribution for any number of ways of any possible distribution. So this equation number 5, that is partition function, you can further rewrite. So this was the partition function that we can further rewrite in this fashion. So z sum over n1 and 2 all possibilities. So these are the number of ways in which this distribution can be achieved. Say one possible distribution can be achieved, e power minus beta and sum of Boltzmann weight. So allow it for all possible to evaluate for a long time. So you can see all possible distribution. In that situation, any state can be acquired by any number of molecules. So you start from 0 to infinity. Any Rth state can be acquired by number of molecules that may run from 0, 1, 2, 3 up to infinity. So this is the partition function, and so these are the number of ways of degeneracy of the occupancy of that particular state. Fine. So NR, you have these are the values. Okay, energy state where Rth energy state where number of molecules can be 0, 1, 2, 3 and so on, and this number of molecules is capital M. So this Z basically this Z which is written here can be rewritten in this fashion, Z equal to e power minus beta epsilon 1 plus e power minus beta epsilon 2 and so on, power capital N. Okay, this can be written because of the fact that NR has this much possibility. Okay, any state can have any number of molecule. Fine, and each molecule are independent to each other, and sum over all possible state is capital N and total energy is capital E, and that is the situation. You can write it in this fashion. Okay, taking log of it, you will have log of Z, that is N log summation over this term, and log summation over R e power minus beta R. Okay, so R e power minus beta R, that is partition function. So this is what you have. Average number of molecule in any Sth state is minus 1 upon beta divided by epsilon s of log of Z, and this was the term that we have seen here. This thing, equation number 7. So according to that, average number of molecule in Sth state, that is minus 1 upon beta divided by epsilon s of log of Z minus n upon beta minus beta e power minus beta s summation over R e power minus beta epsilon R. Okay. So this is what average number of molecule in Sth state is nothing but n upon this term is Z e power minus beta es. So n upon Z e power minus beta es. So this is average occupancy This average occupancy of any state is proportional to e power minus beta es. That is what you have Boltzmann distribution function. That is equation number 1. That is equation number 1. So probability of occupying any energy state at temperature T is nothing but e power minus beta epsilon s. So this distribution function is nothing but Maxwell-Boltzmann distribution function. That is equation number 1. And this distribution can be used to derive physics of any system at high temperature. So according to this distribution function, molecules are identical but they are distinguishable. So this is however this is not true. Molecules are identical but they are indistinguishable. That we will see in the quantum mechanical distribution function. However, this was the first distribution function due to Maxwell-Boltzmann, and it has certain trouble. And however, application of this distribution function will give us some idea of classical approach and some troubles emerging out of it that we can rectify in the quantum mechanical distribution function. So this completes your Maxwell-Boltzmann distribution function. However, this Maxwell-Boltzmann distribution function can be derived also using some other approach.